Hello and welcome to this video that will provide an overview of the installation of IzoT routers applicable to both the EVK and Standalone editions. The target audience is the OEM developer, the network integrator, and to a lesser degree the IT administrator. We will be covering a range of topics that should be useful for you, from background information, the use of a variety of relevant tools, and maintenance topics such as configuring the IzoT router and updating the firmware. IzoT routers allow easy connectivity to head-end apps and cloud services. They are multi-channel, natively supporting free topology, Ethernet, and optional Wi-Fi, and can be expanded with up to 4 external USB modules to provide for 7-channel routing. They are multi-protocol, supporting LON, or classic LON Talk, LON Talk IP, and optionally BACnet IP, and new for June 2015, IP852. Or ISO IEC 14908 Part 4. In addition to the router functionality, they feature the IzoT server with a REST API that allows for custom web page creation. In addition, you can create custom applications in Python. There are 2 versions of the IzoT router, the EVK edition that is supplied with the FT6000 EVK, and the Standalone edition, which will be released in June 2015. Documentation for the IzoT router is available online as part of the wider IzoT documentation at www.echelon.com/docs/IzoT, and it covers a wide range of useful topics. Let's examine a couple of general points before getting into configuring the IzoT router. There is a clear difference between LON Talk IP and IP852. LON Talk IP is a protocol based on UDP that supports both unicast and multicast messaging in an IP-based infrastructure, whereas IP852 is a protocol that tunnels LON Talk packets in a UDP frame that requires the config server app to establish the channel in the first instance. LON Talk IP does not need the use of the config server. If you have an existing installation which includes Neuron Series 3000 or 5000 based devices, you can upgrade it to become an IzoT network by simply swapping the existing routers for IzoT routers. This will then allow the devices to be reached by an IP address. However, they will not support ICMP, UDP, BACnet IP, or SNMP. This would require the network to be in compatibility mode, which is automatically set by the IzoTnet server. Okay, moving on to configuring the IzoT router. With respect to username and passwords, the default router username and password is admin and password. The default server username and password is admin and admin. Other server web pages use IzoT and IzoT. The default secure shell or SSH and secure FTP or SFTP username and password is Debian and Debian. We'll be discussing more about SSH and SFTP a little bit later. You can configure Ethernet and LON Talk DHCP versus static addressing in the Network tab. If you make any changes, a reboot is needed. LON Talk DHCP is configurable in the DHCP tab, and you can set it for either server, relay, or disabled. Again, if any changes are made, a reboot is needed. IzoT router services are configurable in the Features tab, and you can enable and disable items such as the IzoT server, remote network interface, LON Talk routing, BACnet routing, and FT termination. Configurable in the System tab are things such as username and password, IzoT router reboot, and you can reset your IzoT router back to factory defaults. The IzoT server is accessed via the Server tab. You can use up to 4 U60 DIN FT or 4 U60 DIN RS485 or a combination thereof to provide for additional network connectivity with your IzoT router. You can restore IzoT router factory defaults either by using the System tab or by pressing the Connect button and then using a paperclip to press the Reset button. You then wait 10 seconds until the Connect LED starts flashing red, and then release the Connect button, or holding the Connect button down whilst power cycling the IzoT router will achieve the same thing. The IzoT server defaults are set per the IzoT SDK user manual. When installing an IzoT router in a LonTalk IP network, the IzoT router default is to use interoperable self-installation. The default router type is a repeater. However, it can be managed by an IzoTNet server, and the IzoTNet server will automatically configure it for remote network management during the commissioning process. Multiple routers can be used to support large networks, up to 300 devices for networks managed by ISI, or 32,385 devices for networks managed by the IzoTNet server. Each device in a LonTalk IP network has two types of addresses: a host IP address, which is typically assigned by a DHCP server, and a LonTalk IP address, which is either assigned by an interoperable self-installation engine or the IzoTNet server, and it is derived from the LonTalk domain subnet node address. Let's look at LonTalk IP derived addresses. With a domain ID of 0, the LonTalk IP address is in the form of 192.168.subnet.node, and zero-length domains can be set in the OpenLNS object browser. With a domain length of 1, with a value of DD, the LonTalk IP address is in the form of 10.dd.subnet.node. With a domain length of 3, with a value of D1, D2, 00, the last byte must always be 00, the LonTalk IP address is in the form of D1.D2.subnet.node. You can use the LonTalk IP address calculator to convert from one format to another. Here we show this more graphically. Here we have a network with a couple of devices on an Ethernet channel and a couple of devices on an FT channel. The device down here wishes to send data to the device on the Ethernet channel at the address of 192.168.1.23. However, all he does is it sends to the device at subnet 1, node 23, and the IzoT router inflates this address to become a LonTalk IP address as required and forwards it onto the Ethernet channel. Conversely, if this device at 192.168.1.23 wants to send to this device on the FT channel, he sends to the LonTalk IP address, but it gets passed to the IzoT router that handles the relevant subnet, which then extracts the network address and passes it on to the FT channel purely by reference to a subnet and node address. LonTalk IP uses domain broadcast, subnet broadcast, and group addressing, much the same as LonTalk does. LonTalk IP, however, passes network-wide broadcasts, subnet broadcasts, and group addressing through an IP infrastructure using IP multicast addressing. This contrasts quite favorably with respect to BACnet, which has to provide additional hardware devices to achieve the same effect at extra cost. So how does this work? Well, messages with a destination address of 239.192.0.s should be forwarded to the .s subnet. Messages with a destination address of 239.192.0.0 should be forwarded to all subnets within the network. Messages with a destination address of 239.192.1.g should be forwarded to all subnets within the network again. All traffic will use source and destination ports of 2541, and to allow this traffic to pass through the IP infrastructure, intermediary routers should be set up accordingly, and VLANs can be very useful in this particular respect. So let's move on to a quick demo with Wireshark. I want to capture on my Wi-Fi interface some LonTalk IP packets. We don't wish to see anything else that is happening on the network, so I can select options and create a capture filter, associated with port 2541. I can then click on Start. I can then press a service pin, in this instance on an FT-based device, and then we can see a service request going out over the network. And we expand this and we can actually see here that the source address is the 192.168.8.0 subnet, or the 8 subnet, and the destination address was 239.192.0.0, which is a network-wide broadcast. So we will quit Wireshark for the second. Moving back to our presentation. So let's look at mapped addressing. A device's host IP address may or may not be the same as its long-talk IP address, and mapped addressing allows one IzoT device to learn another's host IP address which has been allocated by the IP infrastructure. The first transmission to a device in a peer-to-peer connection will always be sent using a long-talk IP multicast address where the destination long-talk IP address is encapsulated within the frame. The recipient will, however, reply from its host IP address. The long-talk IP address will be encapsulated in the reply, or it will be indicated that the long-talk IP address can be derived from the host IP address. Subsequently, transactions will use the actual host IP address as the target address. So if we looked at a worked example where the host IP address is different to the long-talk IP address, let's say device A has a host IP address of 10.3.124.55. An LNS will assign its address to domain 050600, a 3-byte domain, subnet 1 and node 2. When sending to 05060001/2, LNS or another device will use an IP multicast address of 239.192.0.1 and will include the destination domain and subnet and node ID in the UDP packet. Device A will respond with its host IP address of 10.3.124.55 and will include its long-talk IP address in the UDP packet. LNS or another device type will learn from this that the IP address, unicast address for 050600/1/2 is in actual fact 10.3.124.55. So subsequent messages to that particular device are sent using the unicast address of 10.3.124.55 and include the long-talk IP destination address in the UDP payload. So example number 2 is where the host IP address is the same as the long-talk IP address. So device B has a host IP address of 050613, and LNS will assign a long-talk IP address of domain 050600, subnet 1 and node 3, which just happens to be the same as the host IP address. So when sending to 050600/1/3, LNS will use a multicast address of 239.192.0.1 and will include the destination domain subnet and node ID in the UDP packet. Device B will respond with a source IP address of 05.06.1.3 and indicates that the long-talk IP source address can be derived from the IP source address. LNS or another type of device will learn from this that the IP unicast address for 050600/1/3 is derived, so subsequent messages to 050600/1/3 are sent using the unicast address of 050613 and do not include the long-talk IP destination address in the UDP payload. Now, IP routes tell a device how to reach another device on a different IP subnet when using unicast addressing, and routes are part of a default gateway's configuration, and they can be manually added to a device if it's supported. So, for example, PCs and Linux machines support routes. And if a device does not know how to reach a given address, it will forward the message to the default gateway for the default gateway to handle. And IzoT routers near and far long-talk IP subnets can be found in the Identifiers tab of the router properties in IzoT by looking at the router domains, or by looking at the router's domains table from within node-util. A router's host IP address can be found from the DHCP server or from node-util. And if a router's long-talk IP address is not the same as its host IP address, a route is needed for it to respond to unicast messaging, such as CT's managed test. So here we have our example network. We have two FT channels, here and here. We have two routers. We have an Ethernet and Wi-Fi channel. We have a default router, which is both for Ethernet and for Wi-Fi at 192.168.11.1. And here we see, with the exception of router 2, that every device's host IP address is the same as its long-talk IP address. Again, with the exception of router 2 here, where the two are clearly different. And we've done this for a very specific reason, because it's a worst case scenario for you to understand. So before we can use applications such as node-util or IzoT, we need to set up a long-talk IP interface. And we can do that by using the long-talk IP interfaces application, which is found under IzoTNet Service Utilities, and it's called within that program group IzoTNet Services Long-Talk IP Interfaces. And it allows you to establish a name against a IP interface for your particular machine, much the same as you have a name for a USB interface such as LON1 or LON2 that would be established by the LONWorks interfaces app in control panels. Okay, so the easiest way to understand this is with a demonstration. So let's do that. So here we have the long-talk interfaces application. I can call this one test, and I can select from the drop-down either my local area connection, Ethernet, or my Wi-Fi connection. So let's just select the local area connection, click on create, and as luck would have it, I already have one called test. Let's call this test 99. I will create that and life is fine. And now when we use CT or other applications, perhaps such as node-util, we can reference the name of test 99 for our network interface. Moving back to our presentation. So how do we find the host IP address and the long-talk IP address of our IzoT router? Well, we can do that from within node-util, or from within IzoT, or from within the DHCP server. And we're going to show you each of those in turn. So from node-util, we need to invoke node-util with a valid long-talk IP interface. I have one for my Wi-Fi adapter called long-talk IP. So I will start node-util. I will press the connect button, which pushes a service pin out onto the Ethernet Wi-Fi infrastructure. Node-util receives that. It finds it's a router. I can go to device 1. I can press S for status, and I can see that the host IP address, as opposed to its long-talk IP address, is 192.168.11.19. If I want to see its long-talk IP address, I can look at the domain tables just by pressing on D. I will select both of them. I can see that it's subnet 11, node 19, with a zero-length domain, which is derived to 192.168.11.19. So that's within node util. From IzoT CT, I have my CT drawing. I can right-click my router 1, select properties, and look at the identifiers, and I can see that it's subnet 11, node 19, and its derive address, as we know we're dealing with a zero-length domain, is 192.168.11.19. Okay, from the DHCP service perspective, I have an ASOS Wi-Fi router, access point, Ethernet switch in my network, and I can examine the clients associated with this device, and I can see, if I scroll down my network, that I have my IzoT router here, which has a static address assigned as a permanent DHCP lease. Moving back to the presentation. When we look at IP routes, they're there to allow one device to communicate with another device on another subnet. So in this particular instance, router 1 has a LAN host IP address of 192.168.11.19 and a LAN side LAN talk IP address of 192.168.11.19. So they're both the same, so we're very lucky in that particular instance. And the LAN side, or the FT side, is at 192.168.8.1. So we're dealing with the 8 subnet on the far side of router 1. With respect to router 2, its LAN side host IP address is 192.168.11.53. However, its LAN side LAN talk IP address is 192.168.11.18, which is clearly different to its host IP address. And it has the 13 subnet on its far side, on the FT side. So the routes that we need to establish for router 1 are to the 8 subnet, which we refer to by 192.168.8.0, with a Class C mask, and the gateway on the Ethernet side is the host IP address, as per up here, of our router 1, which is 192.168.11.19. Now looking at router 2, if we wanted to do a unicast message with LAN talk IP for things such as CT's managed test, then we would need a route to its LAN talk IP address, which is 192.168.11.18, with a mask that defines a single device address, and the gateway would be its host IP address of 192.168.11.53. However, in this instance, it's the same subnet as the host IP subnet, and therefore we need to treat this specially in that the static route cannot be in the default gateway. It has to be put as a persistent route in the PC, which we'll show you in a second. The 13 subnet, or 192.168.13.0, with a Class C mask, the gateway in this particular instance is router 2's host IP address, which is 192.168.1.53. Now, routes to different subnets, it's important to understand this are just part of a normal IT setup procedure. We're not doing anything fancy in that particular respect. So if we look at these routes as they are seen in the default gateway, we see that to get to 192.168.8.0, or the 8 subnet, we need to go to the 192.168.11.19 host IP address, and to get to the 13 subnet, we need to go to the 192.168.11.19 .11.53 host IP address. If the long talk IP address was in a different subnet to the host IP address, we may also have a route to the from the long talk IP address of our IzoT router to its host IP address. But that's if they're on different subnets. In this particular instance, that's not the case. So how do we set up persistent routes for PCs? So from a command prompt that's been elevated to administrator permissions, you can't just invoke a command prompt. You have to go Start, Program, Accessories, right-click command, and then run as administrator. The command that we need to put in is route-p add to the destination, which is 192.168.18. The mask in this instance specifies a singular device, and the host IP address is 192.168.11.53. And we only need this in this particular instance because the host IP and the long talk IP addresses are on the same subnet, and ARP address resolution will not succeed in this particular instance. And this is normally handled by the default gateway. If you wish to see existing routes on your PC, you can use route print, and if you wish to delete a route, you can use route delete against that particular target subnet. Just for good measure, we're showing you here how to add persistent routes for Linux devices. You need to add an entry and etc. network interfaces for an IzoT router, for example, against ETH1, and then you need to add one line specifying what happens when the interface is up, and then another line specifying what happens when the interface is down. And then, should you wish to see the existing routes, you can use sudo or superuser do and then route -n. As we can see down here, an editing session in Nano where we've got exactly the up and the down persistent routes added. So if we want to commission our IzoT router with IzoT CT, normally we would use a configured algorithm, or the router type will be configured. However, this will filter traffic. So by way of a heads up, if you want to use NodeUtil from the Ethernet side or from long talk IP, then you would need to change the router's algorithm temporarily to a repeater. There's a URL here that gives you the knowledge base entry on Echelon's website, and we'll show you quickly a demo of how to commission your router and establish the router's type within IzoT CT. If I move to IzoT CT, here I have router 1. I can right click that, I can select properties. In advanced properties, I can see that it's a configured router, and I may, if I want to use NodeUtil, make it a repeater, but you need to remember to change it back after you finish with NodeUtil. And then commissioning is exactly the same as any other type of Lonworks router. Right click, commission, and CT will take care of everything for you. Okay, moving back to our presentation. Using the IzoT router with BACnet. So an IzoT router can be used to translate BACnet IP to BACnet over FT, or otherwise called BACLON, and it allows FT10 based devices to have a BACnet IP interface in addition to their long talk IP, and UDP interfaces. And BACnet routing is an option with the standalone version of the IzoT router. With the release of Node Builder 4.4 in July 2015, Echelon will be supporting BACnet MSTP as well. And the way that we do that is with an external RS485 transceiver connected to the Neuron chip's SCI I/O model, as shown in the following slide. So here we have an FT6050 with its standard comms port connected to an FTX3. We have the GPIO. In this instance, we have IO 7 through 7 and IO 11 because the UART is using IO 8, 9, and 10 in conjunction with an external RS485 transceiver to support BACnet MSTP. Put this in perspective, you can have a device that is running both BACnet MSTP and BACnet IP in parallel. However, you connect to the BACnet IP network through, in the case of BACnet IP, through the IzoT router, in the case of BACnet MSTP, through a BACnet MSTP to BACnet IP router. So if we look at that in a demonstration, if we go back to our IzoT CT drawing, we can see this parallel configuration. We have our FT 6000 EVB number 1, which is connected via an FT channel, and it is supporting BACnet IP, and that can be seen on the Ethernet and Wi-Fi channel. It also has an RS485 transceiver that is used to convey BACnet MSTP via a BACnet MSTP to BACnet IP router, again to our Ethernet and Wi-Fi infrastructure. If I move over to a BACnet client, I can see that my device, which is on network 401, has available a whole bunch of BACnet objects, and the device which is on network 201, which is the MSTP network, again has a bunch of BACnet objects. They're exactly the same because they're using exactly the same mapping table, except they're being exposed on different interfaces. Here we see space temperature from our Lontalk IP network being shown as 24 degrees, and space temperature which comes out direct from the BACnet server, or in this instance our FT 6000 EVB, being shown in degrees F. So here we have two completely different interfaces sharing the same source data, being monitored from our IP side through effectively two separate interfaces. And the key difference here to remember is that where LonWorks or IzoT will send data across the network typically in SI units, and it's up to the person at the end to interpret the data either in, say, SI or imperial format. BACnet servers have to send that data pre-formatted in the required format. So in this instance, our BACnet MSTP interface is sending directly in degrees F. So moving back to the presentation. We can use SSH or Secure Shell to connect to a remote Linux machine as though we were local, but we're doing this over an IP infrastructure. You would use an SSH client such as PuTTY to do that. The easiest way to show you this is to demo it. So let's move over to PuTTY. I have an existing entry for router 1, and I can open that using SSH. I enter Debian as the username and Debian as the password. And here I am as though I was connected locally. I can do ls. I could do, for example, IzoT stat, and I will see after I put in the password the current state of all of the applications running under the supervisor, but I can also see that the IzoT SDK version for this device is 1.02.28 and the IzoT router version is 1.1.7. Okay, so that's how we connect using SSH. You may need that to do an update to your IzoT router. But then again, there are other options available for you. You can download PuTTY from this particular URL. So secure FTP or SFTP is a way of connecting to a remote device and transferring files between both ends in a secure fashion. You need a secure FTP client to be able to do that. WinSCP is an open source client that you can download from the URL shown here. Again, we'll give you a quick demo. Let's get out of PowerPoint, move over to WinSCP. Router 1's host IP address was 192.168.11.19. The username was Debian and the password was Debian. Never save these because it's a security hazard. We will log in and I'm now connected to my PC over this side, my remote machine over this side. It happens to be a Linux machine. I can, for example, I can go to the IzoT SDK and to IzoT and look at the examples and move over to the LED controller. And here, as it happens, is the Python script that this LED controller over here is in actual fact running. Okay, moving back to the presentation. So how do we update our IzoT router software? It's in the documentation. Go to the URL that we gave you previously. You will need to contact support for the relevant download links. The router software also updates the IzoT server. So you have a couple of options to update your router software. You can download and install the update using an SSH console, or you can reflash the complete router with a complete router software image, for which you'll need a bootable USB flash drive. However, this will establish factory defaults and invariably clear out your own user data as well. So in summary, to make this all very simple to understand, for IzoT CT installations, the only things you have to do are to create a LonTalk IP interface for your PC, pick your favored domain length and associated ID, create your network in IzoT CT offnet just as you would do normally, create static routes to far side subnets and near sides of your IzoT routers if necessary, as defined in the IzoT CT drawing, within the default gateway and subsequent paths as necessary. You need to make sure that LonTalk IP multicast messages can pass through the IP network infrastructure. You can then physically install your IzoT routers, your network cabling, and then your devices, and then commission the network with IzoT CT on net by commissioning first the routers and then the devices in the same way that you would do for LonWorks. You can then test the network and then you're pretty much finished. So that concludes this video and we hope it's been useful for you. Thank you for watching it and goodbye.